Okay, so just one more lecture from chapter 11, just to cover a few points that I didn't make in previous lectures and to show you a synthesis problem using some of the chemistry from this chapter as well. So if you wanted to do this synthesis starting with cyclohexane and make this molecule, then we could have recognized, okay, we could have come from a diol. So if these two carbons were attached to each other, and we had that diol, then we could oxidize it using HiO4, periodic acid, which would cleave the carbon-carbon bond, and then you would have it make C double bond O's in its place. And then where the diols come from? Well, from alkenes we've looked at. So if you had this alkene with osmium tetroxide H2S, that would make the 1,2 diol. And alkenes we make from alkyl halides through E2 eliminations. And we could have made the alkyl halide from a free radical bromination, right? So that would be one way to do the synthesis. So that's 1, 2, 3, 4 step synthesis. Although there's actually a shorter pathway, we could have actually gone directly from the alkene to the final product, right? We could have cut off the last 2 steps and did ozonolysis. Zinc instead, if you remember that reaction from chapter 8, how to oxidize an alkene using ozone. So there's a couple of pathways here. So in reality, which one would you do in lab? Generally, you would do the one that's going to be faster and cheaper. So maybe the 3-step synthesis would be faster and cheaper. But in reality, what you're going to do is you're going to do whatever chemical, you're going to follow the pathway for whatever chemicals you have available to you. So if you don't have the equipment that would be needed to do the ozonolysis reaction, then you may go with the 4-step pathway and do the osmium tetroxide and periodic acid oxidation instead. But the basic point is, whenever you propose a synthesis, generally there's more than one pathway to get there, and the shorter the better, if possible, if all of the chemicals or equipment's available. If not, then maybe you take a longer pathway. Okay, so let's take a problem like this. So let's work backwards. So if I give you the products, then predict what was the starting material. So here, if HiO4, the only time that you've seen this reagent is to oxidize a 1,2 diol. So you'd have to recognize, okay, these carbons used to be attached to each other. And that used to be alcohols instead of carbon-oxygen double bonds, right? So that would have been your starting material, 1,2 diol. And then when you do the oxidation, right, you cleave it there, and both carbons get oxidized to C double bond O's. Okay, so a minor point that I didn't make in the lecture over tosylates, right? So if you react alcohol with tosyl chloride, right, it attacks the sulfur and kicks off a chlorine, and you make this tosylate, and then you can bring in some good nucleophile to attack here and kick off the OTS group to make the product. Right, so in this case, the alcohol with the tosylate, right, so you lose HS. It's not the mechanism, but this is just thinking about how to get the product, right? So then that would make this tosylate. And so the point is here is that this is a tertiary center, which means you cannot do SN2 reactions. So if you made this tosylate, you would be forced to do an SN1 reaction to displace the tosyl groups. You couldn't do something like KCN because this is a strong nucleophile, wants to do SN2, and so that's not going to work. So generally better to make the tosylates with methyl primary or secondary carbons. Okay, and then lastly, didn't say much about the mechanisms for oxidation, so I just thought I'd show you the general mechanism, how these reactions work. So if you have an alcohol with chromic acid, for example, H2Cr4, Well, the first thing that happens is you lose a water molecule and you make this chromate. You make a chromate ester, and then this is where the oxidation occurs at. So this is not all that stable. So what happens, a water molecule takes this hydrogen off. These electrons become a carbon-oxygen double bond, and then chromium leaves. All right, so this carbon's been oxidized. So if something's been oxidized, then something's been reduced. Well, so what's been reduced is chromium. Right, so chromium gained electrons. Which the gain electrons is reduction, right? So that's a general mechanism how these oxidation reactions of alcohols work. Okay, and that's all.